a series of online seminars, which I really enjoyed. As you can see, I'm going to talk about state estimation. And actually, part of my talk, I'm going to give an overview of estimation because it's a very diverse audience, with apologies to my systems colleagues like Miroslav. This is joint work with Avneet Kaur, who's my PhD student, and Rukan Zhu, who's another PhD student at Waterloo, and Jun Liu, who's a faculty member. This is just a bit of motivation, these examples of what got me started on this line of research. This is a picture of a lake. This is Lake Huron, which is just north of here. People do, as some of my colleagues do, we have really good models for water flow, Navier-Stokes and so on, and we have intermittent measurements at certain locations, and you want to try and figure out how cold is it, deep down, and what's going on with the currents and so on. And then, oh wait, I have a pointer. And then this was another colleague in civil engineering. We were trying to figure out again with bridges. There's a truss structure here in his lab, Sriram's lab. And then again, you've got a pretty good mathematical model, but it's got some errors in it, and I've got intermittent measurements at certain points on the bridge. And then this is a diagram of a lithium cell, which I did some work on a few years ago on estimation, and that's a really hard estimation problem. Again, we have really only a measurement of the voltage at the terminals, and you want to try and figure out what's going on with very complex electrochemical dynamics. These are actually all PDE examples, which is what I usually work on, but this is actually the last time I'll mention PDEs in this talk, because I realize that the whole estimation issue is really difficult. So just as a basic, really, problem description, I have, and these are all really nonlinear examples. So I have some nonlinear ODE, system of ODEs, and I've got an initial condition, and I've got a measurement. And just for the sake of simplicity, I'll say the measurement Y is a linear function of the state, but the state X, but that's not really important. That's not important at all. What's an estimator? An estimator is another dynamical system which you construct in some way, which has some state X hat, and the key property is that as time goes on, the state of the estimator has to converge to the true state, okay? So the obvious thing to do, if you hadn't really worked in this field at all, was you'd say, okay, I have a pretty good model, so I'll just construct a model of the system and use that, okay? But this is terrible. First of all, if the initial conditions don't match, you're typically, you're not going to get X hat to be an estimate of X, right? And if I knew the initial condition, like if I knew the state at time 0, then I would probably know it at later times, and I wouldn't need an estimator. So this really doesn't work. Also, it's ignoring the whole question of having, can I forward on this? Yes, I can. It ignores the whole question that actually I'm ignoring the fact that I do have measurements. I don't know the whole state, but I do have these measurements, right? So you should use them. So really the best result for doing estimation is for a linear system, which is well known in the systems field. Minimum variance estimator design. So I try and design so that I minimize the covariance of the errors, okay? And supposing I have linear dynamics. And it turns out, and also I have a nice setup. I have Gaussian noise, and the noise on the model and the noise on the sensors are independent, okay? This was solved around 1960 by Bussy and Kalman, and we can figure it out by solving a differential Riccati equation in finite time. And if you take it infinite time, you get an algebraic equation. And at the time, there was actually a bit of skepticism on this because people were saying, oh, you've replaced one problem I don't know how to solve by another problem I don't know how to solve, and this algebraic Riccati equation. But actually now we can solve these with thousands of variables, and that's no longer considered really interesting. But this is what you get. So this is a nice setup. Does this thing have a light on it? No. So I have the noise, right? I process noise, which would be like disturbances or allowing for errors in my model. and I have sensor noise, because no sensor is perfect, right? They always have errors, okay? And the optimal estimator, if I had nice noise and linear dynamics, it's got this really nice form. You've got really a copy of the original dynamics, and then it appears in this really nice for free, even though we didn't pose it in the problem. For free, the optimal estimator is actually in feedback form. So I feed back an error between the actual measurement and the predicted measurement. And what you scale it by, this gain or filter here, you get it from solving this algebraic Riccati equation. And this is really important, is that the error between the estimate and the true state converges to zero. In fact, it converges to zero exponentially, okay? So I'm not actually trying to construct a copy of the system. I'm not trying to identify the system. I'm trying to construct another system with stable error dynamics, okay? And we have that in this nice case, right? And the discrete time case is exactly the same. I just wrote it this way because it's a little easier to explain. But for nonlinear systems, I realized when I started looking at this and thinking about sensor location, can I go back? What if I have nonlinear dynamics, which is most situations? Then there's really not much theory or practical. Typically, I mean, that's an important problem, right? So what do engineers do? The big one is the extended Kalman filter, where we linearize it at each time step, right? And it works pretty well if it's not too nonlinear and your initial estimate is pretty close. You can do unscented Kalman filtering. There's a lot of other approaches, but they're a little, on the ad hoc side. Another thing that people might do commonly is you think, okay, I don't know the optimal form, but maybe what I'll assume is I'm going to feed back the error in the prediction, and I'll try and figure out the optimal F, okay? So there's a lot of sort of numerical approaches, but not much in the way of theory. So the sort of long-term goal of my research at the moment is to improve state estimation for nonlinear dynamical systems, okay? And something that we've been looking at, just what I'm going to talk about now, is using neural networks, particularly recurrent neural networks, to construct minimum variance estimators for nonlinear systems. So I'm curious, like, is this, everyone's very excited, I mean, everybody here, about using machine learning. Is this one of the problems that machine learning could be advantageous to? I know there's been some really good successes in solving optimal control of nonlinear systems with neural nets, so it sort of indicates that this estimation might be another reason. We did some earlier stuff. We looked at Jordan straight Jordan recurrent networks. Here we're just going to compare a Jordan long short-term memory and an Elman type to a traditional Kalman filter, just to see how they stack up. And we have some results on verifying the error convergence. So yeah, so a lot of people have been doing work using neural nets to predict states, okay? So a lot of people will use only the data. They don't have a model, which often is you have to do. You don't always have a decent model. And that's what we called in the old days system identification, okay? So it's a different kind of a problem. What we're looking at here is a situation where I have a pretty good model of the system, right? Not perfect, but I have one. And I have data, and I want to try and have them work together. Can use the most. There's also been some work. I'm not listing all of the specific papers because there really has been a lot of it. A lot of people have been tuning Lunenberger observers, which is basically this, as I sort of mentioned a minute ago. So trying to figure out that F numerically. So you tune it, again, using learning, okay? And I really found one paper, so someone was really using an optimal type approach, but using some theoretical results from Art Krenner from about 20 years ago. But it's got a lot of assumptions. But I guess you'd call that a physics-based approach because it uses a Hamilton-Jacobi-Bellman equation. What we did just here was we tuned the networks to minimize the error variance, okay? So the mean squared error of the estimate, which is a fairly straightforward problem. So the two architectures we looked at were Elman, which are pretty popular, and then an Elman I'm just showing the straight element because the long short-term one is too complicated to drop. What you do in element as opposed to a standard recurrent network is you take the hidden layer from the previous time step and update it. So you're sort of updating the hidden layers here. There's an approximation theorem, which Miroslav was just talking about. It works for dynamical systems, for ERNs. Yeah, and we're focusing on LSTMs because they should be a little more efficient for training. A Jordan network is not as widely used, but we looked at that because it seems much more natural for a dynamical system. Because in a Jordan network, the recurrence is you're taking the output. So what's the output in the system? You're feeding it in the current measurement, right? And then it goes through the hidden layer, and then you get a predicted state, and then that is used to update the loss function, which is the sum of squares of errors, okay? And then we get a new predicted state, okay? And in a Jordan network, that output from the previous layer, which is the predicted state, is used to update things, which is very much how a dynamical system works, right? The state is actually the memory of the system, and that seems a very natural update. So that's why we looked at that. Yeah, that's it. So we just looked so far at 3 fairly standard and fairly simple examples. One was linear because we have the optimal answer to compare it to, the Kalman filter. And that's just a system of connected springs, and we discretized them. So we did the comparison to the discretized system. We're pretending the world is discrete time. So discretized springs. So it's 10 second order systems, so it's 20 states, okay? And there's parameters, and then the measurement vector, we're assuming you could measure all the positions, but not the velocities. And of course, there's measurement noise on the measurements, and process noise is included in this. I just didn't write it in, okay? Before someone asked me, so what are we using as data for training the network? Because we have the model, is we have the true state, right? So we give it various initial conditions and various noise sequences, and you can use the true state, right, as well as the measurements in training it, right? And then hopefully going forward, it can predict the actual state. The second example was like another classic one, the pendulum, right? And we used Runge-Kutta 45 to discretize it. There's parameters, and the measurement is just the position, right, plus noise. And third example was a reverse van der Pol oscillator. It's another second order system. Again, we just measured the position, a noisy position measurement, okay? And here's a table, what did we get? So the normalized mean square error. So for the linear example, we compared it to a Kalman filter result, and they look better, but that's just over the data we used, right? But pretty comparable. And then we compared the 2 nonlinear examples to the results for an extended Kalman filter, which is based on linearizing around an initial condition. And it's actually significantly better than extended Kalman filter, which was encouraging, suggests this is actually worthwhile. But what was even more encouraging is we did testing with initial conditions well outside the training region, right? Because the idea, this is really why you want to be using the model in constructing an estimator, is that hopefully you end up with an estimator that will give you reasonable predictions outside of where you were able to train it with data, right? So that if something happens that you didn't already have data for, you're going to get a reasonable prediction. So anyway, we tested it with initial conditions outside of the training region, and there, okay, the Kalman filter is way better for the linear example, which is not surprising. But both the Jordan and the Elman networks were much better than the extended Kalman filter, which is suggesting that it's actually learning the nonlinear system much better. So that was good. And the training time, this was something that we need to look into some more, but The Jordan system seems to have shorter training time, which is indicating that maybe the architecture is better for learning a dynamical system. Something we need to keep looking at. And then testing time, not very surprising, is that the neural net is much, and people talked about it this morning, right? The neural net is much faster than the traditional architecture, which is one reason for looking at this, right? Because eventually, if you're doing this on a real problem, you're going to want it to run in real time. So you want something that's not only accurate, but will compute quickly, right? You're not, maybe even on, like someone talked this morning about FPGAs. Okay, so summary so far, right? We tested Jordan and element networks on 3 examples and compared them to with traditional approaches, and they seem to work really well. Particularly on the nonlinear system, they were better, which is good. And Jordan seems to have a smaller training time, so we're going to continue looking at that. So now I want to talk about stability of the aerodynamics. So remember, again, we're not just trying to copy the system, right? We're trying to get something where I have stable aerodynamics. So here's the system. Oops, hang on, let me go back. Okay, so there's my system, and then here's just generic, right? So my estimator is some other dynamical system with the measurements as an input, right? So then the aerodynamics, and this is written in discrete time, right? It's the difference between the true and the estimated states. So we end up with this. This is part of the problem of establishing stable aerodynamics for nonlinear systems, because in a linear system, the measurement part separates out really nicely as an external input, whereas here it's mixed up in the dynamics. So if you look at that, you think, okay, we can regard this, I shouldn't have a hat on, it's just the error, right? So you could eliminate x hat from the expression, right? So now I have an expression for the aerodynamics, right? And I can regard x, right, the true state, as the input for the point of analyzing the stability, okay? So I'm going to regard x as the input, and I'm going to assume the estimated system is stable, which makes things better. And it's actually reasonable because a lot of natural systems are stable, number one, and number two, if they're not, you're going to construct, you heard about in the previous talk, you're going to construct a controller using state feedback to stabilize it, and then the estimator is another step. Okay, so we're assuming the system's stable. Okay, so this is, we'll get into ISS, which is some work done by Eduardo Sontag, who's speaking later this afternoon, okay, which was really the key to getting this to work. If the error system is input to state stable and the origin of the estimated system is stable, right, then the origin of the cascade system consisting of the estimator plus the original state is going to be asymptotically stable, okay? So how are we going to do that? This is a bit of stability theory for the rest of the room. I'm going to go real quick. So a continuous function is a k function, basically if it's increasing with the argument, okay? In k infinity, it keeps going up. And then a KL function is increasing with respect to the first argument and decreasing with respect to the second argument, okay? So it's what you want for a stability Lyapunov function. You want the state to go down with t, right? But for it to be reasonable, it has to be unbounded with the first argument, which is the state, basically, okay? So there's a nice criterion for input to state stability, which is if there exists a KL function and a K function so that this inequality holds for everything, okay? So that's like a nice theoretical result, but we can actually use it here because you can translate them into inequalities, okay? And inequalities are nice criteria for working with on a computer, okay? So it's going to be an ISS Lyapunov function if first of all, V, okay, is bounded above and below by K functions of the error state, right? And this is the one that means that it's ISS, right? So that subsequent time minus the previous time is less than or equal to some negative K function plus gamma, okay, on the state. So what we tried to do in the last stage, and Rukan was a lot of this work, is here's my estimator. So my estimator, and we just did this with a simple JRN network, okay? So we have a really simple neural network with one hidden layer here, okay? So then the aerodynamics look like this, right? The original dynamics minus whatever the neural network's out to being, okay? So I have another discrete time system. Hang on, let me go back. Okay, so I need to find an ISS function for that system. Okay, the Lyapunov functions are inequalities, right? So what we do is two stages, actually. So we're going to try and learn, so there's a second part of the neural net part, which is that we're going to try and find a network that will be a Lyapunov function. So we're going to try the neural net to learn a Lyapunov function, okay? This is based on earlier work of Chang in 2019, and then also Junliu Yuming Wang, who was an earlier student of John's, and Mike Fitzsimmons and Rukan Zhu. So anyway, so we have a fairly simple feed-forward neural net, okay? We have weights and hyperparameters, okay? So we're going to solve for the hyperparameters. There's two stages here, okay? So the first step is the network tries to find weights to minimize the loss function, okay? And this is designed basically, you penalize, the loss function penalizes violations of those inequalities, right? So if that ends up being positive, you're going to end up with something that it thinks is a Lyapunov function. So that's stage one, okay? And then stage two is verifying that it actually works, okay? So we check what's called falsification constraints. So you set up a series of inequalities, which if they are satisfied, it's not a Lyapunov function, okay? And this we can do because it's actually a very specific kind of function, very specific class of function. So we can use a satisfiability modulo solver, okay? We use DReal here that can check to see if it's possible for these to be satisfied. And if it returns false, then you can be assured that that's in fact a Lyapunov function. So that's stage two, okay? So we can recap. I think I'm done now, right? So if I can recap this stage, oops, let me go forward, right? The first stage was to learn an estimator, okay? And then the second part was to check that it is an estimator in that it has stable aerodynamics. And to check whether or not we have stable aerodynamics, you first tune a totally different neural network to learn a Lyapunov function, and then check to make sure that in fact it is a Lyapunov function, okay? So this is just work we've done the last year. We're gonna work on reducing the training time. We have a better computer coming. And we wanted to work on higher order systems and explore whether or not Jordan really is the right architecture to be working with, and extending our work on establishing stability, which as I mentioned is key for an estimator for actual JLS TMs for like more complicated architectures. Just as in control, right? Like in control, often we're trying to find like an optimal control, but more important than optimality is stability in the control system. It's the same thing in estimation, right? Like I'd like to find an optimal estimator, but if the aerodynamics are not stable, meaning I'm not converging to the true state, then it's like toast. So sometimes maybe you might want to settle for suboptimal but reliable. So, and we're also going to look at what I guess would be called a physics-based approach. Maybe we can bring in some HJB here. So that's it. So thank you.